Hi and welcome to my new video. Now in my previous video I showed you an example of a voltage regulation. We did all this stuff. I don't know what I showed you what's an ideal transformer, what's a practical transformer, what is the no-load short circuit test, voltage regulation, and now I'm going to talk about efficiency of the transformer. Now you all heard, well, energy is neither created neither destroyed. It just transforms in one shape into the other, and etc, etc. And that is true, but if the energy is not even created or not even destroyed, what is efficiency then? Why isn't efficiency 100? Well, to put it easily, we as an electrical engineers, we measure the efficiency of only electrical powers. Now, the efficiency eta, I think you all learned that, is defined as the output power divided by the input power. Now, the efficiency of a transformer is very huge, and because it's a static device, it doesn't have any rotating or mechanical parts, and it doesn't have any air gaps as in rotational machines. It doesn't have friction and ventilation losses. So in transformers we only have electrical energy. But in machines such as AC/DC, synchronous machines, we have mechanical power also. So in transformers, the efficiency, which is this letter called the eta, this is a Greek letter, and it's equal to the output electrical power divided by the input electrical power. So if you have 10 kilovolt ampere on the input and you have 9,5 kilovolt ampere on the output, you have 95 kilo divided by 100 kilo, sorry, let's say it's 195. So this deletes and you get 0.95 of efficiency. In percentage, that is 95%. Now, what this means that 5% of the input power is lost due some heat or something else that is not electrical, and those 5% we call losses. Of course, the efficiency of a transformer can be less or higher of 95%. It can't go above 100%, and it can't go less than 0%. Either it would be some kind of a generator. But in transformers we have from 0 to 100%. But in real transformer never has 100%. There are always some losses. Now, then what is the input power? So input power can be defined as the output power, P out, plus the power of the losses. So we will have some losses. We generated some energy into the system on the primary side, and there are some losses. For example, the core loss and copper loss or windage loss. And then the efficiency therefore can be written as the output power divided by the output power plus the core loss. So this is the core loss and this is the copper loss or windage loss. So this this is the formula that is usually used. Now, we have copper loss and we have a core loss. Now, the copper or the windage of the transformer, it has a primary and a secondary side. If we are talking about one-phase transformer, we only have one windage on the primary side and one on the secondary side. So the copper loss by Joule's law is therefore I1 squared times the resistance of the primary windage plus I2 squared times R2, the resistance of the secondary windage. Now, you know that if we transfer these values, for example, from secondary to the primary, then we have I1 secondary, R1 plus I2 prime squared times R2 transfer. Now, I1 squared and Y2 prime squared are the same value, and then we get, because if you transfer it from the secondary to the primary side, then you get I1 squared in brackets R1 plus R2 prime, and this here is the equivalent resistance looking it from the primary side, and this here is the equivalent resistance looking from the secondary side, and this is what are we going to use, I2 squared times R equivalent to. Okay, so this is the copper loss. As you can see, usually the resistances of the well-designed transformer is same, it's constant. But in real life, as you put more current, it heats up the windage, it heats up the conductors, and then if you have higher temperature, this will rise. But let's say that this is a constant. It doesn't rise that much if the windages are very good. And how do we calculate the active power of the output, the power output? How do you calculate it? Well, this is from electrical engineering. You have the phase voltage times the current I2 and times the power factor cosine theta 2. So, but if it was a three-phase transformer, you would just bring here number 3, multiply this by 3. But it's not three-phase now. You don't have to worry about it. And also, if you bring here number 3, you need to know that this is a phase voltage. If this was a line voltage, you then multiply by square root of 3. Now, so we can rewrite this formula over here. We see that the power output is equal to the phase voltage times the secondary current times cosine theta 2. This is the power factor of the the load, and then we can rewrite this formula like this. So V2I2 cosine theta 2, V2I2 cosine theta 2 plus the core losses, which can be measured easily with the wattmeter in the no load test, and I2 squared R equivalent to. Okay, now in my previous videos, previous two videos, we showed that this V2 can go up and down, but usually it's a constant. It doesn't go very much up and down. It's usually a constant value on the secondary, and the the load terminal voltage is usually constant. And if you say that the theta 2 cosine theta 2 is a constant, then you can see that the efficiency of the transformer depends on the load, so of the drawn current on the secondary, and it's mostly that situation. The core losses on a if you have a constant voltage on the primary and on the secondary, the core losses always stay the same. And in my next video, you will see what is the maximum efficiency of the transformer. So please watch my next video, and I'm going to explain you what is the maximum efficiency of a transformer. Thanks for watching, and see you in my next video.